thank you guys for being here. I think there's some really interesting things that we want to get into. Tim, you've been clear. This isn't telepathy. This is unfortunate, but it's not telepathy between the device and the body, although to the common person, that's what it sounds like. So what is this? What exactly does it do?
Well, yeah, it's not telepathy, but it's the next best thing.
Yeah.
Right? So what our interface platform does is it enables bidirectional communication between digital devices and the nervous system. I'm going to put that in simpler terms. Messages go from your brain down to your muscles and your organs, tell them what to do. We read those signals, we decode those signals, and we can translate those out to a digital device. Then, in return, we can actually send messages back up to the brain or improve the messages and send them back down to the muscles or the organs.
Okay. Well, expand on that. So, I mean, how do you even begin here? How do you even measure what kind of signals are coming out of whatever muscle and how that interacts with the brain? I mean, as I understand it, we have still a pretty rudimentary understanding of how the brain works and where those signals even come from and what they look like.
Yeah, Jake, you want to
let alone how to manipulate them.
Sure. Yeah. So you're totally right about the brain. The brain is a mystery, right? That's one of our grand challenges, to try to unlock and understand that. One of the advantages of the technology that presented here is that we're avoiding the brain on purpose, right? The brain is difficult to understand, but the peripheral nerves are actually much easier to understand. They're a simpler system. The peripheral nerves send these digital pulses down these, what we call biological wires, right? You think of an electrical wire essentially, and it sends a single digital pulse down to, for example, your muscle, and that will cause a contraction, and you send these pulses faster and faster, and that will cause your muscle to then contract. Okay. And that's what creates your dexterous movements, right? The pattern that goes on in the brain is a little bit more complex, but once it goes down through your spinal cord to your peripheral nerves, it becomes a much simpler problem to solve. And so essentially we put a device in the peripheral nerve, and we can listen to those digital pulses that are coming down and then interpret them into what a person's trying to do, like moving their hand or grabbing an object.
So where give me a sense of where the devices lay on the body.
You bet. So we implant an array of electrodes right into the median nerve and the ulnar nerve. Okay. That allows us to interact with the cells directly. So you got your nerve fiber that does one job. Either it's sending a feeling of touch back up to your brain, or its job is to cause one tiny little muscle group to contract. Okay. And so we can listen to those individual signals. And we got it.
How do you listen to them?
Well, we just put a little voltmeter. That's what that electrode is. So we're just measuring the voltage.
Tiny little voltmeter. You know where the nerve is. We've known where the nerve is for I guess some time now.
Yeah.
Basic anatomy, and then you just got it. You're listening to it.
Yeah. So and then we take now. It's easier said than done. We're taking data in at 30,000 points per second. And we're doing that on up to 300 channels at a time. So it's a huge amount of data.
Right. So it's I can't buy the voltmeter at Home Depot. It's not that kind of voltmeter.
No.
So it's like there's all this other innovation that had to happen before you got to this point, to where you can even measure it.
Yeah, and that started decades ago, where there's some key groups in the country that were like, hey, we want to bring movement and feeling back to amputees.
Yeah.
Right, simple as that. And one of those key groups was a group led by Dr. Greg Clark at the University of Utah. Now he's the one that got the DARPA funding, not us. Just to be clear, because that was a lot of work that they put in. But he was working with DARPA and with other groups, for decades to move this along. And that's where, in the meantime, a group of a little more seasoned industrial folks, myself, we've got Wendy Wong here, our Chief Operating Officer. We're coming from these large corporate backgrounds of knowing how to move this stuff to bring it to market. But we needed people like Jake, like Dr. Clark and others to really get it to the point where we could take it and do something with it. So we formed a BIOS, and we brought Jake on board. He got his PhD working with Dr. Clark at the University of Utah. Okay. Licensed the technology Jake had done, and we've built a prototype using the cutting edge AI software and hardware that's available today.
Do we have like a video or something of the prototype we can see?
Unfortunately not. We've
Then you'll have to describe it really well, or picture or something. And so what does it do? I mean, what's the patient experiencing?
Let me just see if we can watch this one more time. It's a good video, so let's, if we can, there we go. What we're doing is we're measuring these signals with no batteries in the body, just little voltmeters basically.
Okay.
And it comes outside the body into what we call our controller. And that controller is the one that is treating the data, filtering the data. It's measuring the important things of it.
This is a surgical implant. You got to get that in just right. And
That's right.
Okay.
Yeah. Now the great thing is it's outpatient, right? There's a lot of other, Neuralink is obviously big in the media now, but there's people further along like Synchron, Paradromics, BlackRock Neurotech that are going right into the brain. We're talking about an outpatient surgery that really takes minutes, minimal scarring.
Yeah. This is also how Iron Man suit gets built, isn't it?
It is. We can certainly go there, and technology-wise.
Why not?
Where this can go.
In theory, it could be easier.
Yeah.
More inputs, right? And then boom, I'm Iron Man.
Well, yeah. So
I get to be Iron Man first, since I had you at my healthcare summit.
We are happily accepting any volunteers that want to join our studies. So,
Deal.
No, because we can certainly go into where this technology can go.
Yeah,
And
well,
it's
clearly for amputees. Now, I have one question, which
Yeah.
is, because of the peripheral nerves that you use, you read them essentially. Does that only really work for your limbs, your legs and arms?
Well, no. So one of the other, it's a whole other system in your body, the autonomic system. So like your lungs breathe, your heart beats, your pancreas does whatever your pancreas does.
Yeah. Who knows?
Sure. But there's nerve signals that are sent to all of these organs to allow them to function. There's even in immunology, there's impacts from the nervous system. And so one of the great things that what our platform is we're not trying to go and solve all these problems. What we're trying to do is provide a platform to let researchers today could work with our development kits and work with our developers and actually start trying to solve all these different problems that are out there.
I see. So you're creating like a baseline code, I guess, and see what people can do from there.
It's a toolkit.
Is this FDA approved? What's the journey like here?
Yeah. So the journey, we're at the front side of it from application to the FDA. So we're submitting for breakthrough designation. We think we're going to get it. The great thing is we've been able to reference a lot of excellent work at the University of Utah and other places where they've gone through the animal trials, they've gone through human studies. We're up to, I think we just had our 8th human study. So we're able to leverage a lot of that information to try to get there faster. Because I'm an engineer. Background's actually in computer chip manufacturing, which that's one of the fastest paced industries out there. And so to go from that place to here's 2 years of FDA work, or 3 or 8 or 11 years of FDA work. It's a rude awakening.
It's a constant, It's a constant frustration when you come to these summits because you hear about these cool things and but it's not really available. It'll maybe in 20 years.
And I'd echo what we heard earlier as well, which is the FDA is the first barrier, but there's this whole other barrier that exists beyond that, which is the reimbursement side.
Yeah, we were talking about that with CMS. Yep.
Yeah, and the CMS is arguably the harder barrier because in a lot of ways the FDA wants to protect the patients, right? They want to make sure it's safe, but they also want to make sure that it's providing some benefit. Whereas in CMS, a lot of their interest is making sure that it's financially going to have some sort of value, right? They're going to save money so that this person isn't spending or costing them money elsewhere. And that becomes a real challenge in our
It is for us too, because
right?
that person is the taxpayer, and Medicare is already by far our biggest, I don't know if it's our biggest, but Medicare, Medicaid, Social Security together are by far our biggest expenditures. When we talk about debt, 70% of all your federal spending is those programs. And we don't actually even touch them every year. So it's a real concern, but there's got to be a more creative approach where you say, well, but this could save us a lot of money in the long term.
Yeah.
Innovation is such just general, you think about innovation, how much, look at the eye surgery I had to save my eyesight. People don't realize that my good eye is not a good eye at all. It's a really messed up eye. It's aphakic. I don't have a lens in it. But we have these surgeries, you know, people age beyond 60, whatever, and you know, they get a cataract surgery, and it's like no big deal. And you just replace the lens inside your eyeball. Should have seen the surgery they did to my eye to save it 2 years ago. It's catastrophic looking, honestly. It's disgusting. But they did it, and it's amazing. But with normal human life, over the course of thousands and thousands of years, was just me just being blind. That's normal, was to just be blind after you get your face sprayed by a bomb. And the cost associated with that, I wouldn't be here now. I would need somebody to take care of me all the time. It'd be a totally different cost trajectory. So, I agree.
Yeah, that's one of the challenges we face, is trying to find, you know, that's the next step, right? Is to demonstrate not only that this device is something that patients want, but that it will reduce cost, right? And I think the challenge we face is that we're ahead of the curve. So if you take a system like this that we're showing, where a person has, you know, this bidirectional control of a bionic arm and can feel from it, and you take them in and have them perform a standard clinical test. The way these tests are performed right now for upper limb dexterity is you take a bunch of blocks and you move it from one side of a box to another as quickly as you can. And if you do it with this, it's just as fast as a hook. And so the question is, well, then it's not good, or what's going on here? But sure enough, if you replace those blocks with, you know, delicate objects like eggs, you can't do it with a hook. It turns into this huge mess of broken eggs everywhere.
Yeah.
But when you do it with this bionic arm, all of a sudden they can do that.
Right.
But that's not a clinical test that exists. And it goes beyond that too, because we've had cases where we have this individual who's using this device, and after, you know, using it for some period of time, we ask them what they want to do, and they respond to us that they want to clasp their hands together. And this is an individual who's controlling a prosthetic arm and has their own intact biological arm on the other side. And they say they want to clasp their hands together. Now all of a sudden, this is no longer, you know, a prosthetic tool that they're using. It's become almost equivalent in their mind as to their healthy hand. And they sit there and they massage their hands back and forth.
Interesting. And you can actually feel that sensation,
and they can
feedback.
feel that sensation, and
Weird.
they can move it when they think about moving it, and they can get a sense of touch back from it. And all of a sudden, we have to think about, wow, this is amazing technology. But you can't take that video to CMS and say, okay, this is what patients want. This is what they need. Look at what this is doing for this individual.
Right.
But we have to now turn that concept and that patient gratification, right, that we see in like a photo like this, and boil it into something that CMS can determine as a code and a value, right?
Yeah.
And there's good news here too, right? So with the work that we've done, with the work that from the University of Utah, is we're really looking at a few years out before we can get this out and into the marketplace, where people can choose if this is what they want for them. You know, we're working really, really hard towards that. And it's studies like this, it's participants like this, when you see the look on their face and you see the difference it makes, you know, it motivates our team certainly to work as fast as we can.
Yeah. It's interesting. I'm curious what you see the future holding. At one of our summits, we had researchers from Rice talk to us about what did seem a little bit more like telepathy. So they were basically reading the signals coming from a mouse brain, and then letting the mouse see what the mouse saw, and based on those signals, they could tell that's the color blue. It's this. I mean, this is related technology. You know, so you get to a point where. I think that was also on some DARPA funding, because, you know, from a military mind, you're thinking secure communications between people by just thinking. Is that where this could possibly lead the further you develop it?
Yeah, potential, and that one's pretty far, right? Person-to-person telepathy, but you know, when you look at
My wife reads my thoughts.
yeah, well, I'm
It's horrible.
Yeah, I'm a lucky man that way as well. You know, when we look at the fact that we're communicating in the natural language of the brain and the nerves, and we've got this mountain of data, it's not just about helping people with limb differences, which, you know, great thing in itself, but you know, like I mentioned before, there's just a host of other health conditions that can actually be affected. But this is where, you know, there's a medical summit, so don't go too far off here, but, you know, what happens when you start thinking about, say, remote operations, hazardous environments, or in surgery rooms, right? So rather than
Right.
having to run a joystick, what if you were connected directly?
Yeah, there's a reaction time issue there that
Yeah.
it could be, again, Iron Man suit.
Yeah, well,
that's really
that's-
what you were saying without
Yeah.
saying it.
Well,
Iron Man
and
suit.
you know, there is a defense picture up here. That what we found is we can actually do this faster. We can translate those messages, intercept them high up enough on the arm. We can translate them faster than the time it takes for the message to actually go through your nervous system in the first
Wow.
place.
Yeah, so your technology is specifically the ability to translate the message. What people do with that, you're like, hey, go for it. What's the difference between, I didn't get to ask this question, and we're out of time, but
Yeah.
we'll wrap this up. I haven't heard about Elon Musk's Neuralink in a while, but what's the difference between that and this?
Sure, yeah. So I think the big difference is where the interface is placed. So Elon Musk's Neuralink is trying to place a device in the brain. This has some advantages and some disadvantages. Placing it in the brain is one of the only areas you could get signals for an individual who might have a spinal cord injury, right? Those signals are blocked at the spinal cord, and so they're not coming to the peripheral nerves. So our technology might not be able to help that understand what that person's trying to do.
Oh, interesting.
Or a person with like ALS, for example. But the challenge of going into the brain is that, as you mentioned earlier, the brain is really complicated. We don't really understand what's going on inside of the brain. So trying to write some algorithm or some AI software that can interpret what's going on in the brain is still very far out. And we don't understand what's going on there. But if we go further out, it's much easier to understand. The other challenge is that, as you can imagine, we've had participants that have been willing to say, like, sure, you can put this in my residual limb that's been amputated, and I'm not using it anyway. I don't think anyone would say that about their brain, right?
Yeah, and we'll have another conversation. I'll see how realistic Neuralink even is. I mean, or is it? Like I said, I haven't heard about it in a long time, but this is your field, so. Does it ever have a chance of coming off the ground and having interesting applications?
I think definitely, yeah. They've made some groundbreaking progress in hardware and engineering technology. They've really kind of moved very quickly into an FDA trial. I think that really shocked a lot of the neurotechnology people in this area, how quickly they were able to move into that space. So there's definitely some promising things, and I always, as a scientist...
Is that because it's only a receptor and doesn't transmit something?
No, I think, sorry.
Or does it transmit?
The technology that...
Yeah, the Neuralink. Does it only... I didn't mean to make this about Neuralink, but now I'm curious.
Right now, it's mainly just recording, right? So
Right,
it's
the
sending
receptor,
information
yeah.
out, not necessarily putting information in yet. But I imagine that they'll be able to do that as well. I think...
And then you have mind control, and that's what people are freaked out about. And then he owns Twitter. Oh, God.
So there's some great applications and some good promise there. I think the one thing I like to say, as someone who's been in this field for a while, is that there are, still areas that we know a lot about and a lot of areas that we don't know much about. And one of the areas we don't know much about is like memory and communication and things like that. And so, it's much harder for someone to be able to just like read your mind than it is currently. But to be able to understand what a person's hand is trying to do based off of their peripheral nerve signals has been done since the 60s even.
Really?
So we've been doing that for a while.
And the bottom line really here is that, there's a mountain of data traveling through our body every second of every day. And the ability to tap into that data and connect it to the digital world, and then to be able to control that world, I mean, the possibilities really do feel endless. And I love thinking about the impact we're going to have, the capabilities we're going to add to mankind, the suffering we're going to be able to alleviate. We really hope this is going to change the world.
Hope so, too. Thank you for being here. This is fantastic. Thank you. Appreciate you.